Welcome, folks, to the last lecture on attacks and pitfalls. Today, we'll talk about the so-called Spectra Attack. Before we do that, though, I'd like to say that, of course, it's not possible to cover all the attacks in that chapter, but I would recommend that you also read about the GSM, the old GSM phone system. There is a good example of a system that, on one hand, was a huge commercial success. On the other hand, though, was essentially a security failure, and how that's actually possible that both things happened at the same time. It's a good lesson on how the real world sometimes works. And also, I recommend you read about the Backdoor Pseudo-Random number generator, which is a kind of scary example, actually, of how apparently the NSA, the National Security Agency in the States, influenced international standards by placing a weakness in this pseudo-random generator that would, when used, for instance, in TLS, would enable the NSA to easily break into internet traffic without having to break the encryption. Okay, but as I said, today we will concentrate on Spectra, which is also an example of a very broad class of attacks, which are important to know about, and also in some sense pretty scary, because they draw into question the whole way in which we design CPUs, and seem to point to the fact that maybe efficiency has been overemphasized at the cost of security. So before actually talking about the attack, we need some background on CPUs and memory. Yeah, in the old days, it used to be the case that the standard model of a computer would be you have the CPU, which is where actual computation takes place. There are registers, and you can execute instructions and so on. And then on the other side here, we have the random access memory, the RAM, and this is where all your data is stored. And whenever the CPU asks for something, it sends for an address here, and then the data comes back via the bus. And that was the way it was for many years. And then what happened was that CPUs got faster very, very quickly, and memory did not get faster that quickly. And this becomes a problem because when the CPU asks for data, then it has to wait for a long time. At least it seems a long time from the CPU's point of view, because the time you have to wait until the data arrives can sometimes correspond to several hundred instructions. So it seems you waste a lot of time. Okay, so then what was invented was something called a cache. So this is basically also a piece of memory, smaller than the RAM, but much, much faster because it's on-chip together with the CPU. And now the idea is that we are not going to do things quite this way directly to the RAM. Instead, the CPU asks for data down here. And when you fetch data, then of course, eventually data comes from the RAM. But the point is that when you fetch data into the CPU's chip, you will not only, so let's say the CPU asks for an address here, and the address that it asks for is here in RAM. What you're going to do is not to fetch just the data at that address, but also a little chunk of data which is sort of in the neighborhood of that address. And then this gets fetched into cache. And the hope then is that in addition to the CPU getting the data that it wanted in the first place, the hope is that next time it wants something, it's probably in the neighborhood of where it asks in the first place. So therefore, in that case, so when you have the next address, the hope is that this thing will also be in cache now. In this case, you have the so-called cache hit. You could also get unlucky, of course, and the address, in fact, doesn't point there, it points somewhere else, so that maybe, in fact, we wanted something out here, in which case you have a cache miss. So here's a hit, and here's a miss. All right, so in case you have a miss, well, what happens, of course, is that the system goes out and gets a new chunk of data out here and brings this to cache. But now, of course, we have to wait until this happens. Or do we? So now enter the, in some sense, the villain of the game here. The thing is that in order to save time while waiting, or to spend the waiting time with something useful, CPUs do what is known as speculative execution. And what this is that the CPU guesses what it should maybe be doing after the data that it asked for comes back, and it just starts doing it. So an example of this is, let's suppose that the code you're executing contains an if statement. So if some condition here that depends on a variable x is true, then something here, right? So whatever is here should be executed if that condition on x is true. So if x actually is out here and not in cache, then you have to wait until x comes back to actually evaluate that condition. But the CPU can make a guess. For instance, it could be that based on earlier executions, say you come back to this piece of code several times, it could be that this condition has been seen to be true all the time before. And then a reasonable guess probably is that this condition is also going to be true this time. And so the CPU will say, okay, I believe that's true. So these executions, these instructions that are here, I'll just start executing those. And then, of course, at some point, so now we're down here, say with the execution, now X comes into the cache and can be seen by the CPU. You can evaluate the condition. And if the condition is true, then you've actually, you're ahead, right? Because you've already done some of the stuff you're supposed to be doing here. And you've saved time. That's great. It could also be the condition is false. In which case, of course, what you've done here should not have happened. So that means you now have to roll back your state. So if the condition, let's summarize here, if the condition is true, that's great. We have saved time. If the condition is false, well, then you have to roll back. So meaning that whatever state the CPU is at this point down here where you got to, you have to roll back to the place here. And the way you do this is that when you start the speculative execution, you save a copy of all the registers and everything that's on CPU. And then you restore to that value if you find out that what you did down here actually should not have been done. And that's fine. However, so why is it fine? Well, because if your guess was right, the condition was true, you've saved time. If the condition was false, well, at least you're no worse off than if you had just been waiting the whole time. And this really works well. You see examples of speculative executions of several hundred executions, and it means really a lot to efficiency of modern CPUs. So it really buys you a lot of time. There is one caveat though, because let's say that this speculative execution here, let's say that it at some point does something that requires data, and here you encounter a cache miss. So that means at this point, of course, the CPU has to start ordering data from RAM to be put into the cache. So let's say that was this piece of data here. This gets fetched into cache, okay? And now the CPU figures out that the condition was actually false. I have to roll back. Then the registers on the CPU, they do get restored to the old values, like before you did the thing that should not have happened. But the fact that this item was fetched into cache here, that thing is not rolled back, because this would be way too inefficient to do this. And also, you might say that why should this be a problem, yeah? Right? Because the data is not wrong. It happens to be in cache instead. So what? I mean, that's fine. Maybe you need it later on. What's not to like here? You'll see what's not to like later on. But just for now, I just wanted to notice the fact that this speculative execution has a side effect, namely bringing something into cache. And this is something that would not have happened if it were not for speculative execution. If the CPU had just done the naive thing and just waited until the data came back, this cache miss would not have been encountered, and this piece of data here would not sit in cache. Okay, and that's actually something that's not quite in keeping with what this code here that you execute, what that really means, because it says if the condition X is true, then you do this, and otherwise nothing happens. So something else happens. So whatever side effect comes out of this code down here should actually not happen at all, but still it does. So let's have a look at how an attacker might be able to exploit this kind of thing. So okay, I should say, by the way, that the Spectra Attack, which is our headline today, Spectra Attack is a type of attack that talks about CPUs that serve several different users. So if you're in a multi-user system, you have user 1 here, you have user 2 here, then both of these guys may use the CPU. And of course, for the operating system, it's now very important that the processes run by the first user are separated from the processes run by the second user. It should not be the case that different users can read each other's data just because they use the same CPU. And we'll see that Spectra is actually about trying to break this separation. Okay, so yeah. One thing to notice, by the way, maybe I should say this also here on this drawing here. So one thing to notice is that, let's say that user 1 here is the bad guy, give him some horns and stuff here, and this guy is the good guy up here. One thing to realize here is that the attack doesn't have to be only about what happens inside the CPU. It could also be about what user 1 can do to user 2 with external means. So what I mean by this is that, for instance, user 1 could send user 2 a message or do something else that's external to the computer, but this might make user 2 run a process on the CPU with a certain input that might depend on the message he got from user 1. So in this way, if we want to take all this into account, we actually have to assume that user 2, the program he runs, actually runs with some input that could be chosen by user 1. So that's actually something that we have to take into account when we talk about what can we do in this environment here. So let's remember this for later. Okay, so now let's say that we have user 2 here. So the guy who is, was that the guy I wanted to attack? Yeah, that's the guy I wanted to attack. Fine. Okay, so we have him here. He runs a program. And let's say, for example, that the program contains the following little piece of code. So it says, if X is less than array 1 size. So I'll get back to what all this means actually, but if that's the condition, then, oops. So then, what do we want to do? What we want to do is the following. We want to say set Y equal to array 2 indexed by a value which is array 1 indexed by X times 4096. So the reason for this funny constant, I'll get back to that in a moment. That's what we do. So not much there, but the important. So let's go through in a moment. So X is an index, and it's supposed to be used as an index into array 1. So therefore, this condition here makes sense. This is the size of array 1. So we're basically saying if X is not too large, it actually points into something that actually is inside array 1. Then we want to do this. And what we do is that we say we fetch this data inside array 1 here at index x. We multiply by 4096, and then we use that as an index into array 2. Okay, so I mean, not too complicated. So how would an attacker try to exploit this piece of code? So the idea is that we have U1 on the other side here. He's the bad guy, and he knows that user 2 will probably be running this program that contains this piece of code here. And I should say, by the way, that we haven't seen examples of the attack so far in the wild, but we have seen proofs of concepts where people have constructed code that could be attacked using this methodology, and actually has demonstrated that it does work. But the conditions are quite special. So user 1 here, the bad guy, really has to hope that there's a very special piece of code inside user 2's program, such as this one here. Okay, so so user 1, we assume, can choose x, okay, and make the program run several times, perhaps, or at least make that piece of code run several times. So the thing user 1 now has to arrange to happen is that so user 1 arranges that let's see, so the x and array 1 is in cache, but on the other hand, the other variables, so array 1 size, which I should say is a variable and not a constant, and array 2 as well. These guys are not in cache, right? And furthermore, the CPU, that's at CPA, sorry. So the CPU, furthermore, thinks that the condition in the if statement is true or will be true. Okay. So that's the assumption that somehow the user 1 can arrange for these conditions to be true by making user 2 run this program with appropriate inputs and stuff. Okay, so if you can arrange this, now U1 is going to choose a large value of x. So he chooses a large value of x. Why would he do this? Well, because the goal he has is to get the value that sits inside array 1 at index x. And why would this be interesting? Well, because array 1, well, that's basically just something that points into user 2's memory at some position. But if you can choose x to be arbitrary and not inside the boundary of array 1, then this array 1 x value here can basically be more or less any piece of data that sits anywhere in user 2's memory. So if you can get to read array 1 indexed by x for any x, then you can basically, in principle, at least read almost the entire memory of user 2. And that, of course, was definitely not supposed to happen. Okay. So let's see how this might be possible. Okay, so what is going to happen at this point when we get to this point here? The CPU encounters this if instruction here. Well, the first thing that happens here is that the CPU notices that, yes, I have x available, but array 1 size is not available. It's a variable that sits out in RAM. So the first thing that happened is we want to fetch array 1 size. Okay? And then we, because the CPU believes, as we said, that this condition will evaluate to true, maybe because this piece of code has been run many times and all the time X was in range. So the CPU starts executing. So you start doing this Y is assigned to, and so on. So the statement inside here. Okay. Now, the thing is that array one is in cache, and X is also in cache, and of course this is just a constant. So this index here, you can easily evaluate immediately. There's no delay there. And now you have to figure out what is array 2 indexed by that value. And of course, array 2 is not in cache, so you have to fetch this thing. So now you fetch this array 2 here, indexed by, and so on, which is what we have up there in the code here. Now the reason for this multiplying 4096 onto this index here is because if you do this, then you actually make sure that this one element from array 2 that is asked for here is the only value that will be fetched. It's a technical thing that if this multiplication by 4096 was not there, then you might get a whole chunk of elements from array 2 being fetched, and the attacker doesn't want this to happen. And so you have to hope that some scaling like this is actually in the targeted program. Okay, so what happens now is that this the CPU will start to fetch this one element from array 2 into cache, and then of course the array 1 size will arrive, right? I mean, we started this whole thing by trying to fetch this thing, and then while that's happening, we start doing all this other stuff. So at some point, array 1 size will arrive. The CPU will realize that, oops, X was actually too large, so there's a rollback executed here. But of course, the point is that while we were doing this stuff, we started fetching this one value from array 2, and this will, of course, will complete. So we will now be in a situation where we have, if we draw an image of the cache and the RAM. So array 2 is here. It's an array with a whole bunch of different values, and then one of these values, the one that we asked for in this code here, will have been fetched into cache, but it's the only value which is in cache. Okay. Now you have to realize that if we could find out if the attacker, so now we have user 1 here, that's the bad guy again. If he could find out which value from array 2 is in cache, then he would be in business, I claim. And why would he be in business? Well, simply because if you remember back, which value was it we fetched from array 2? We fetched a value which is on index this array 1 of X times this constant there. So what I'm saying therefore is that, for instance, if it turns out that if the value we have in cache turns out to be array 2 indexed by, for instance, 4096, if that was the case, so this value here is actually array 2 indexed by 4096, then this would imply that array 1 of X must have been 1, right? And that's your answer. So why is that the case? Well, because if we figure out that what we just said implies that the index here must be 4096. This can only happen if array 1x here is actually equal to 1, right? Okay, so so that means therefore that by finding out which index for array 2 do we have inside cache here, this will tell us the value of array 1 indexed by x, and that was the thing that the attacker was actually after, because that's the value, this guy here, that's the value that by choosing x, we can make that be pretty much any value in the targeted user's memory. Okay, so here you have to take my word that in fact there are ways in which another user can figure out what is in the cache. That's somewhat long story that I'm not going to go through here, and it's also a different type of attack than what we've been talking about. But basically, the point is that because the cache is one piece of hardware that's shared by all the users, all user processes, you can actually figure out what value is in cache. Just to give you an example, suppose, and this is a lot to hope for the attacker, but let's assume that somehow you could make the targeted user, so user 2 here, you could make him execute now a piece of code that would, read the first value from array 2, the second value, the third value, etc., etc. And then so the idea was, so the idea is user 2 reads all values in array 2. So what I mean is you fetch them all into the CPU sequentially, one after the other. And then user 1 measures the time for each fetch. And why would this tell him something? Well, because if you start from the situation where all of array 2 is in RAM except for one value, this guy here, then of course when you fetch the first guy, it's going to be slow because it's in RAM. This thing is slow, this thing is slow, but this one thing is fast because it's already in cache. And therefore this will tell user 1 which of the values were in cache. This is a very simplistic form of the attack because it really it depends on user 2, the targeted user, doing exactly what you want him to do. But there are more advanced ways to do this that will actually tell you what the value is without quite so much, collaboration, if you will, from the targeted user. Right. So this is kind of the end of the story of the attack. It basically says if you have code, such as what we looked at here, that is sufficiently well structured from the attacker's point of view, you can exploit these side effects of speculative execution to actually read, in principle, arbitrary data from the other user's process. So that's not so good. And the problem, of course, here is that the reason why this attack is possible is the speculative execution, and basically nothing else. I mean, so you have to hope that user 2 executes a vulnerable program. But the problem, of course, is that finding out what is vulnerable is a very hard thing to do. There have been attempts to design compilers that would try to detect when code might be susceptible to this kind of attack and then restructure it so it doesn't happen. But it's very, very difficult to completely do this. Of course, the easy ways out of this would be to just turn off speculative execution. But if this cuts performance by a factor of 2 or 3, which it might easily do, then that's probably not what you want to do. So the jury is still out on what should actually be done here. Spectra and its sister and brother attacks came out a couple of years ago and do some pretty big headlines at the time. But I would say it's fair to say that we still don't really have the final answer to this. And it may be that we just have to accept that the performance improvement on CPUs cannot go quite as fast as we thought it might be able to. Okay, so that's the end of this. I hope you enjoyed being scared by these attacks here. Okay. Thanks.